welcome to the next chapter of discussion, which is optical measurements and nanometrology. Today we are more focused towards nano, because nano is 10 to the power minus 9 meters. We are trying to have more understanding of material, process, behavior when we look at this very small scales. So, we will try to cover how does the measurement happen at such small scales, and also how is optical measurements going to help us in this measurements field. So, the content of discussion is going to be introduction, followed by it we will have optical measurement techniques, optical interference, then interferometer, different types of interferometry, and then we will have scales, gratings and reticles, then finally we will have nanometrology to discuss. Let us first try to understand light. Light is an electromagnetic radiation. Okay. It falls in the wavelength between 400 nanometer to 700 nanometer. So, the elementary particle that defines light is the photon. Okay. And when we try to understand a wave, so this is called the intensity. And this is called the frequency. Okay. So, what is intensity? So, in light there are three basic dimensions of light. So, light has only three basic dimensions. One is you try to play with the intensity of light. So, intensity is otherwise called as amplitude, which relates to your brightness. I would say perception, right? Perception of brightness. Then frequency is otherwise represents as wavelength, which relates to color, and I repeat, it is again a perception. Okay. The last one is polarization, which is a very important parameter. There are a lot of instruments which work on this polarization, which is nothing but the angle of vibration. These are the three dimensional parameters for light. So, if you can play with it, tweak with it, tailor it, so then you get whatever requirements you want. Polarization is angle of vibration. So, these are the three basic dimensions of light. When we talk about the properties of light, we have reflection, we have diffraction, which is nothing but scattering of light, of light around the edges of object. Okay, that is diffraction. Then limit of resolution. Then it is refraction, which is nothing but bending of light when there is a change in medium. Okay. So, here we always talk the principles that lenses use to focus light. For example, you can use air, then you use oil, so which changes that. Then use in contrasting techniques. So, we also use refraction principles. Diffraction and refraction are different. Then we will look at interference, which is exhaustively used. A lot of applications today, if you want to measure the linear displacement, we use interferometric techniques to measure. So, here the light wave can be subtracted or added so that you get whatever you want. And the last one is polarization, which I said last time also, it is the vibration. So, allowing only light of a particular vibration plane. This is very, very important. Lot of applications are reflect the polarization is used in optical lenses. They are also used in spectacles. So, these two, whatever we have discussed till now, is the basics of light. Light is an electromagnetic radiation, so you can play with it. It falls in the wavelength of 200 nanometer to 700 nanometer. The elementary particle that defines light is photon. So, lasers work on the principle of this photon, energy packets. So, the light can be basically can have basic dimensions are three things. One is intensity, frequency and polarization, and the three principles is the reflection, diffraction, refraction and interference are some of the properties which are used, properties of light which are used for developing instruments for measurements. So, optical measurements provides a simple, easy, accurate and reliable means of carrying out inspection and measurement in the industry. It is predominantly non-contact. So, once it is non-contact, then it gives you a flexibility of measuring very small resolutions. So, it can also be played very easily. For example, you have understood the properties, you can play with the properties to get whatever information you want, and it is very reliable. Okay. Scientists used an interferometer to measure the path difference of light that passes through a tremendous distance in space. We use interferometers. They measure the wavelength of light in terms of meters. They soon realized that it is made more sense to define a meter in terms of wavelength of light. So, first they defined the wavelength in terms of meters, then they started defining a meter in terms of wavelength because it was very accurate. In the introduction, we also have two things which I already discussed. One is refraction, the other one is going to be diffraction. So, here if for example, you have a droplet of water, this is how the light is passing. So, then what will happen is it will try to pass through and bend. So, this is light from source we will put. This is a medium of low refractive index. So, you can see the light bends. So, this is called as it is cutaway of the object and then it bends. So, it cuts and then it bends. Okay. So, when I talk about diffraction, you will have a source of light coming, then you have a slit. So, you can see light going by. So, the light will pass through several of these sources, okay, and you can see this is a light source. So, here what happens is you can have two types of images. One is constructive image. For example, you have one light coming like this, the other light is also of the same thing. So, then this is equal to a constructive, you can have added or constructive fringe patterns, and when you want to do subtractive, you can suppose you have two wavelengths of light coming like this and here it is on the other way around. So, then what happens when these two are added, so you will always get something like a very low subtractive. So, this is subtractive interference pattern which is given, this is additive interference pattern it is given. So, you see the wavelength is added, the amplitude is added, the amplitude is subtracted. Okay. With these techniques you can try to play with light. So, let us look at a principal device which is a microscope which is exhaustively used, which works on the principle of optics. Microscope in general couples two stages of magnification, the objective lens and then it is there we have one magnification, the other one we will have at close to the eyepiece. Okay. The objective lens forms an image of workpiece at L1 at the stop. The stop frames the image so that it can enlarged by the eyepiece. View through the eyepiece and enlarged virtual image I2 is obtained. So, magnifications at each stage multiplies, thus highly effective magnification can be achieved with only moderate magnification at each stage. So, the most important thing is magnification at each stage gets multiplied. When you look at it, this is what is I1 which I told you. The objective lens forms an image, this is objective lens, so this is objective lens side, okay. So, here you have, so the image objective lens forms an image of the workpiece at I1 at a stop, then the stop frames the image so that it can be enlarged by the eyepiece. View through the eyepiece and enlargement happens at I2, this is I2, okay, this is I2. So, then finally, this is the objective lens, and this is your eyepiece. So, you try to view like this, this is the stop whatever we have talked about, this is the eyepiece, this is the objective lens and here is the plane and here is the work. So, magnification can happen at several stages, thus highly magnification can be achieved only by moderate lenses. Essential features of an optical instrument should have a light source, a condensing lens, a suitable stage or a table to position the work part, then projection optics comprising lenses and mirrors, then screen for viewing, and then measuring and recording devices. These are some of the essential parts of an optical microscope. You can see here an optical microscope. So, an optical microscope, we have this is a light source. So, light source hits it, then there is a beam splitter. So, then it moves towards the workpiece. So, here is a workpiece, and then the workpiece is resting on a table which can go in x and y direction. You can move it, and then the light gets reflected back. So, then there is a reconstruction happening, a fringe is happening, and that is recorded at CC, charge coupled device sensor, it is getting done. So, in this optical microscope, it is also interesting to note that they also have a touch probe. So, it is used to give a rough estimate, or a low resolution measurements can be done here, and then we get into optics wherein which a high resolution can be done here. So, light source for coaxial surface and ring illumination. So, there is a light source which comes, and then this is a touch probe which can go. The sensor heads with the Z direction. For focusing, you can move the, so this portion takes care of the focusing, and this XY tries to take care, X and Y, they try to take care of the traverse of table. So, that means to say you can measure the entire workpiece. So, this is an optical measurement sensor setup which is used today for measuring the height in nanometer level. Heights can be measured. A simple projector is a basic device used for measuring angles with optical magnification, is one of the most widely used techniques in metrology. However, optics has three major applications. In alignment application, we use optics. In interferometry, we use optics for measuring the distance, and it is also used as absolute standard for length. That is what we measured. The length 1 meter is measured in wavelengths today. So, these are the three other basic applications of optics in measurement. The most commonly used one microscope in the shop floor is ToolMaker'sMicroscope. Amongst the microscope used in metrology, we are most familiar with the ToolMaker'sMicroscope. A ToolMaker'sMicroscope supports a wide range of application from shop floor inspection and measurement of tools and machine parts to precision measurement of test tools in a measuring room. So, it is used in shop floor for measuring the small deviations, and it is also used in tool room. Okay. So, here it is more predominantly of tools, here the other items we use this ToolMaker'sMicroscope. The main use of ToolMaker'sMicroscope is to measure the shape, size, angle and the position of small components. Okay. Here we talk angle accuracy in terms of degrees, the shape depends on the stage what you traverse. Size, what we talk about is, we talk close to 0.01 millimeter. The position of the small components also can be measured by using the ToolMaker'sMicroscope. It features a vertical support column which is robust and carries the weight of all other parts of the microscope. It provides a long vertical working distance. So, Z, so that means to say you can keep a large workpieces there. The workpiece is loaded on a XY stage which has a provision for translatory motion in two principal directions in the horizontal plane, that is X and Y, and then the micrometers are provided for both X and Y, so that as and when you move you see the micros. So, what they are trying to say is you have a table, so here you will have a micrometer. So, whatever this rotates you can measure it at a very small accuracies. So, this is a typical ToolMaker'sMicroscope. So, this is the column which tries to take the load. So, here is the clamp. So, this gives you a freedom of this motion up and down. So, you also have a focusing knob. So, this focusing knob and the clamping screw helps you to for height measurement adjustments, and then you have a table. These are the micrometer scales which are there. So, this is for Z measurement, and here you have a X and a Y table for movement. So, this is in micrometer, this is for longitudinal, this is for transverse direction, and here is the illumination. This is nothing but the light source. There is a light source, this tries to fall on the object which is kept here, and then you try to measure it, and then try to see what is the change in shape, size, angle, and even the dimensions of very small components. So, in a tool maker's microscope, you will always for alignment purpose, this is very important, alignment of cross wire in reading. So, you have to measure the flat portion, or the land, okay, which is called as a land if you want to measure. So, first what you do is you put the focus, you at the eyepiece, you will always have this as a cross wire. So, this cross wire is aligned to one side of the one edge where the land starts, and you have to move it to the other end of the land starts, and then you try to get the readings. Okay. So, here you should also understand there are magnifications also there. So, you can have at the eyepiece 10x, 20x, okay, and then objective you can have 2x, 5x and 10x. You can see the working distance. As and when the objective x increases, the working distance goes small. So, this is a very important parameter you should know. When you try to look at very high magnifications, you should understand you are sacrificing the working distance. So, these are the different types of illumination you can have, and more details about the tool maker's microscope. Contour illumination can be done. This type of illumination generates the contour image of the workpiece and is suited for measurement and inspection of workpiece contour. The illuminator is equipped with a green filter. So, now that you can also try to place, I have said 3 basic parameters. One is wavelength, amplitude, and then you have the polarization. If you can play with these parameters, then you can try to get more clarity in the image whatever you have used for measurement. Suppose if there is a workpiece which is too complex in nature, so what we do is we try to make a contour of it, put it in the eyepiece, or have a projector and then have it as a mask there, and then project the screen, project the workpiece dimension. So, you can easily do comparison and try to also measure the deviations. The surface illumination, this type of illumination shows that the surface of the workpiece and is used in the observation and inspection of the workpiece. So, shows the surface of the workpiece, surface illumination. The tool maker's microscope, what we showed you here is surface illumination. So, instead of this surface illumination, you can have contour illumination, which is the first thing which we discussed. Okay. The angle and the orientation can also be done of the illuminator, should be adjusted so that the workpiece surface can be observed under optimum conditions, and then simultaneous contour and surface illumination is also possible. Suppose this is A, this is B. So, this is nothing but A plus B, both contour and the illumination can be done simultaneously to measure the tool workpiece deviations. What are the applications? It is used in shop floor inspection of screw thread, gear and other small machine parts. Its application includes precision measurement of test tools in tool room. It helps to determine the dimensions of small holes where micrometer cannot be used. It facilitates template matching inspection. So, it is something like a comparator. It enables inspection of taper of small components also. So, so basically what it says, shape, size, orientation and XYZ coordinates can all be measured using this tool maker's microscope. Thank you.